Well, hello, good morning, team. Let's put everything together we've been looking at with liquids and solids, and let's take gases from first semester general chemistry and put them all together in one fell swoop on one pressure temperature plot, right? We've looked at vapor pressure curves, just looking at liquids and gases. We looked at sublimation curves, just solids and gases. We talked about melting and stuff. We didn't do effusion curves because, pressure really doesn't influence those too much, at least noticeably under conditions we're normally at in the laboratory, but we'll talk about it briefly here. But let's put them all together now. All three states, gas, solid, and liquid. Those are your three states, right? But phases are a little bit different, right? You might have the solid state, but you might have a bunch of different types of solids, which are called different phases. We'll see that with ice. You can have ice 1, ice 2, ice 3. So phase is going to be a better term for us when we're looking at phase diagrams, right? Even though people use phase and state interchangeably. But technically, state is either liquid, gas, or solid, and a phase could be multiple forms of a solid typically. So we're going to plot pressure versus temperature, just like we looked at before with vapor pressure curves and sublimation curves. But we're going to show all of the phases of a particular substance, right? Under, reasonable temperatures and pressures, right? And what we're going to do, we're going to use the sublimation curve, right? Which shows the equilibrium between the gas and the solid, right? So we're going to show that sublimation curve on this phase diagram, and that represents where those two phases coexist at equilibrium. And if you cross that line, that's a phase transition, right? We'll take the vapor pressure curve, which we've seen before, which is the gas with the liquid. That shows the equilibrium where those two phases coexist, liquids and gases. And if you cross that line, that's a phase transition, whether you're going this way or this way. We'll see that on the graph. And then we'll throw in the fusion curve as well, which shows the equilibrium where the liquid and the solid coexist at the same time. And if you cross that line, a phase transition occurs, either from a liquid to a solid or solid to a liquid, depending on which way you're going. Is the temperature increasing or you're decreasing? And once we put all these together, we can take a look at that and we can journey through this phase diagram. We can change temperatures, pressures, and see how phases change, what kind of transitions can occur on that process, right, around the phase diagram. So let's draw just kind of a generic one to show you where the different phases would be. I'm going to make you think about that, and then we'll pop in these fusion curves, vapor pressure curves, and sublimation curves. Let's do it. Get your pencils and, well, colored pens or pencils or whatever you do on your computer ready to go. All right, let's think about the basic construction of a phase diagram. It doesn't matter. We're just going to do a generic substance right now. No specific temperatures or pressures. If we pick water, carbon dioxide, or something like that, we can put specific pressures and temperatures on there. But let's think about what's happening, okay? So we're at low pressure here, high pressure here, low temperature here, and high temperature here. Well, think about what's happening, okay? Let's think about pressure, right? Pressure, you're cramming those particles closer and closer together. So what do you think is going to happen as you get to higher pressure? Squishing them together, squish. What phase of matter do you think would most likely exist at really high pressure? Probably a solid, where they're crammed together like that. And if you're at low temperature, they're moving slower and slower, intermolecular forces are more likely to lock into place. So when you're at low temperature and high pressure, you're more likely going to have a solid. Okay, so the solid region falls up in here. Right? Lower temperatures, higher pressures. Okay. Now let's think on the opposite end of it. If we're at a high temperature, lots of thermal, lots of kinetic energy, right? More likely to disrupt or completely break the intermolecular forces. And if you're at lower pressures, more spread out, what phase are you thinking there? Gas, right? So at higher temperatures, lower pressures, you're more likely to have a gas. So over here would be the gas region. And of course, at intermediate pressures and temperatures, you're probably going to have the liquid region. Right? Or phase. Okay? So now we can pop in our boundaries here between them. So let's use the brown one here. So we're going to, separating the solid and the gas would be the sublimation curve, right? So we can pop that in there real easy. So the sublimation curve is going to be running about like so. All right? And that'll end at some point. And that's going to separate the solid from the gas region. That's your sublimation curve. So let's put that here. So sublimation curve. Now I may ask you on a quiz or exam to construct a phase diagram like this. You just have to think about what phases are more likely to exist at what particular temperatures and pressures. Now what separates the liquid and the gas? That's the vapor pressure curve, right? So that's going to come through more like this. So that's my vapor pressure curve. I'll just go VP. And so anywhere along that curve, you have both the liquid and the gas coexisting at equilibrium. If I cross that line, like here, if I'm here and I go to here, I'm going from a liquid to a gas phase. If I'm starting here and I go to here, I'm going from a gas to a liquid region. Would that make sense if I'm increasing pressure on a gas? Whoa, right, at some constant temperature. Well, if I'm at constant pressure and I'm going from a lower temperature to a higher temperature, boom, right? You can boil it and vaporize it, all that fun stuff. And then what separates the solid from liquid? That's the fusion curve, which is usually more of a straight line-ish, right? Because it's not hardly dependent on pressures at all. So that's going to go a little more. Yeah, most species have a slightly positive slope, but you're only going to notice that at really, really high pressures. When you're at atmospheric pressure, this is essentially a straight line. Okay. So do you see the breakdown of the different regions? So this will be the fusion curve. Boop. That shows that boundary. So if I'm starting here at some pressure and I go across that line, increasing the temperature, it melts, right? Goes from a solid to a liquid. Or vice versa, if I'm at some pressure on the liquid and I cool it, it solidifies, right? It freezes. Same thing here. If I'm at some pressure here and I'm in the solid region and I go across at that pressure, boom, at higher temperature, it sublimes, it doesn't melt. So this point right here is a really important point to look at, right? Because depending on what pressure you're at, if you're below that point and you increase the temperature, it sublimes. But if you're above that point and you increase the temperature, it melts and then boils, right, into a gas. Interesting. So that's a key point. Now, do you see right here? So these lines represent the coexistence of two phases: liquid and gas, solid and liquid, solid and gas. 3 phases coexist at that point. It's a very unique point. That right there is called the triple point. That's pretty easy, right? The triple point. That's where 3 phases coexist at the same time. Right? We'll define these on the next board. I just want to point these things out. In the next board, I'll write that, define it, define some of the other major points. I just want to point out the points here. Now, there's another point right here. This kind of just keeps going up. But the vapor pressure curve does end. It's something I haven't talked about yet. This point right here where it ends is called the critical point. So we're going to spend some time talking about what is kind of unique over at that critical point right there. Now, what's interesting is when you get past the critical point, if you're at a temperature higher than this, right, and a pressure higher than this, what the heck is up here? That's really, really weird. So I'm going to write this in real quick, and then we'll talk about that when we talk about the critical point. But up in here, so right here, if you go down, right there, we'll go T sub C. That's your critical temperature, okay? And right here, going across, you're just reading the graph. That's your critical pressure, right? So you got the critical pressure here, critical temperature here. Those correspond to that critical point. So if you're at a pressure above the critical pressure, right, and a temperature higher than the critical temperature, you don't have a liquid or a gas. You've got this really unique state of matter called a supercritical fluid. We'll talk about that when we talk about the critical point real quick. But let's put this up here. You've got this region where you have a super. I wish they picked a shorter word. So right up in here, you've got that region called a supercritical fluid. I've never dealt with one in my entire lifetime because you're at high pressures and high temperatures, okay? But it's kind of neat, right? We'll talk about it a little bit. So if I say draw a basic phase diagram, show me all the phases and regions and important points, right? So I want all the vapor pressure curve, sublimation curve, fusion curve that shows the coexistence of the two phases, the solid phase, liquid phase, gas phase, triple point, and a critical point, all right? And another thing we'll be able to read is if we have a pressure of 1 atmosphere, we can actually read normal boiling points, normal melting points, and whatnot. But from this, you can get the critical temperature and critical pressure. You can also get the triple point pressure and the triple point temperature. You can read those off the graph. TT, right? So triple point temperature. So that's a unique point where all phases coexist. That specific temperature, that specific pressure. Personally, I've never seen that. It'd be kind of neat to look at. So if you had a sealed container and you had just the right amount of substance, you would have the liquid, the gas, and the solid all coexisting in equilibrium at the same time. Kind of cool. So let's define the critical point and the triple point on the next one, and then we'll talk about normal melting points and normal boiling points. All right, so some real quick definitions. I've already talked about it. Again, the triple point, right? That region where the fusion curve, sublimation curve, and vapor pressure curve all intersect. That's the unique spot for whatever species it is, and every substance has its own unique values of triple point temperature and triple point pressure, right? Which can be measured in a laboratory, but sometimes the pressures are kind of weird. And again, that's where all three phases coexist. Kind of neat, not really applicable for us, but kind of a neat spot, right? The merging point. Critical point, again, that's the end. So you're drawing the vapor pressure curve, and where it ends, I like to draw a little dot there. That's the critical point. So the temperature at that's called the critical temperature. The pressure is the critical pressure. And if your pressure's above that and temperature's above that, what happens is the liquid and the gas phases kind of cease to exist. They kind of become indistinguishable. They merge together. So the liquid, it's like you've got a gaseous, liquidy thing, supercritical fluid. So it's kind of got the density more like a liquid, right? Not like a gas. It's more like a liquid dense-wise, but it flows. It's less viscous like a gas. It's a really unique thing. And up in that region, there's no boundary between the liquid and gas. They are neither. They're both. Okay, it's kind of weird. And supercritical fluids, we're not going to use at the undergraduate level typically, but you may have heard of them being used as solvents to, I think, decaffeinate coffee, because that supercritical fluid, because it's more dense, you can actually extract, and it's nonpolar, you can extract caffeine from coffee beans, not 100%, but you can get a lot of it out of there if you're at the right temperature and pressure as a supercritical fluid. And once you extract a lot of that caffeine, then what you can do, remove the coffee beans and then alter the pressure or temperature, right? And you can no longer you can get it out of the supercritical fluid region, remove the caffeine and recycle, I think it's carbon dioxide actually, supercritical carbon dioxide. And you can recycle it, right? Extract the caffeine precipitates out, you've got the carbon dioxide back, make it a supercritical fluid again, get some more caffeine. Hey, it's very environmentally friendly, better than using some of these toxic solvents they used to use. So let's draw another phase. So do me a favor, draw another phase diagram with all the three curves. That's not three. All the three curves, critical point and triple point. And let's take a look at how we can distinguish where the normal melting point and boiling points are. And that would be at 1 atmosphere, right? All right, you ready? Let's take a look at it. So generic vapor pressure curve, right? So here's our sublimation curve, fusion curve, vapor pressure curve, some generic pressure, temperature. Now, when we're looking at the normal, right, melting and boiling points, that's at sea level, 1 atmosphere by definition. So what you do is you find where 1 atmosphere is on the scale. So let's say we're at 1 atmosphere right there. Okay, it's going to make a really big difference where that triple point is on what happens. Now let's take that 1 atmosphere and start increasing the temperature. Now, if you stay at constant pressure, that's called an isobar. ISO, same, bar for pressure. So let's take a 1 atmosphere isobar and start increasing the temperature. You ready? You can do this anywhere on any phase diagram. It's really cool. You can just follow the journey, see where you go. So if we're increasing the temperature along an isobar, we would be in the solid region, right? And you would just be increasing the motion of the solid, right? And then it would hit the fusion curve right there where the solid and the liquid coexist, so it starts to melt. And then the temperature stops increasing until it completely melts, and then you pop into the liquid region, right? So if we follow a 1 atmosphere isobar, we go boom, and we hit this liquid region, right? Let me move that up a little bit. That point right there, if it happens to be 1 atmosphere, if you track that down, is your normal melting point, right? Where it melts at 1 atmosphere. Typically, that'll be, for most things, the same as the triple point in this scenario. I just have a kind of an overly positive slope here, but typically that line under these conditions is going to be straight up. So normally those will be the same. So this is not trying to scale in any way. If we continue heating it, now we've got a liquid, right? We're following that 1 atmosphere isobar. The liquid motion's increasing, and then we hit the vapor pressure curve, and it starts to boil, right? So now we've got an equilibrium between the liquid and the gas, and if we keep heating it, right, temperature stays constant until it completely converts into the gas phase. And then you just keep increasing the temperature of the steam at that point. Well, if it's water, the gas. If we take this down, take 1 atmosphere, intersect the vapor pressure curve, that would be your normal boiling point. Pretty easy to read, right? We'll just combine. So we had looked at just this curve and this curve previously. So pretty simple. So it depends where that 1 atmosphere is. But what if we have a different scenario? Let's do this one in green. What if we had 1 atmosphere down here below the triple point, right? So if 1 atmosphere is above the triple point, that isobar where it crosses the fusion and the vapor pressure curves gives you the normal melting points and boiling points, like I wrote up here in purple. But if the triple point is above 1 atmosphere, so if 1 atmosphere falls down here, you're never going to cross the fusion and vapor pressure curves, are you? You're only going to cross the sublimation curve. Oh, that gets interesting. So let's look at a different scenario now. Let's move the 1 atmosphere down here. Let's follow the isobar now. Let me erase these. And if we go and follow an isobar across at 1 atmosphere here, we would cross the sublimation curve. You would never melt in that scenario, okay? So at this point, it would sublime. So that would be the normal you hardly ever hear that term, normal sublimation point, right? But in that scenario, that substance, right, as you at 1 atmosphere, if you're increasing the temperature, boom, it sublimes like dry ice or iodine or something, and then converts into a gas. Boom, 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 boom. That just gets more and more thermal energy. Pretty crazy. So where that triple point is, reference to 1 atmosphere, really makes a big difference. Okay? But you can do this for any pressure, right? I could pick any pressure I want. So if I wanted to actually liquefy this substance, I'd have to come to a much higher pressure. Boom. And then it would melt. Now, if I'm up really high, what if I'm way up here? What if I'm way up here? That's super high pressure. And I take an isobar across. It would melt, right? And then you would hit the supercritical fluid, right? You'd never see the gas, right? Because it's just too high a pressure. So you just can't have that gas phase. So it would melt here, and then that liquid would just, and you'd never see like a meniscus between the gas and the liquid. It's kind of weird. You would just see the viscosity of that liquid increasing. The density might drop a little bit. It still say high density. And once you hit in here, you'd convert it to a supercritical fluid. That would take a really high pressure for most substances. But if I went here, I could follow an isobar across. That's where it melts for that particular pressure. That's where it vaporizes for that particular pressure, or it boils, and you can measure the temperatures at which those occur. It's such a useful plot, right? You can also take an isotherm. So if an isobar is a line of constant pressure, what would an isotherm be? A line of constant temperature, right? Just some terms for you. So, for example, what if I took that point right there in black, and I say I'm going to stay at that temperature, constant temperature, and I'm going to follow a line straight up? That's an isotherm. What would happen? Okay, well, here I'm in the gas region, right? So I've got a gas, and that gas right there would convert into a solid as I increase the pressure. So it would undergo deposition. And then I would just have a solid, right? Unless you have a solid that has multiple different phases. We'll talk about polymorphism in a second here. Right? But if I was over here, and I take this isotherm up, I have a gas. Right there, it hits the vapor pressure curve, condenses into a liquid, and then up you go. But if I'm over here, above the critical temperature, am I above the critical temperature there? So here's the critical temperature. So if I'm above, at an isotherm above the critical temperature, I've got a gas, but it never condenses. It never condenses. It just becomes more dense, okay? And then becomes kind of a mixture of the liquid and gas, that supercritical fluid with the high viscosity of a gas. I mean, the high density of a liquid and low viscosity of a gas. Neat. I mean, I'm making a mess of this, but you can follow any isotherm and any isobar you want. You're good to go. You can see the phase transitions that can occur. Right? So let me pull up a scenario. Let's put up, well, water might be a little weird at first because it's got all these weird phases of solid. Let's get an actual substance, put it up there, and take a look and go, well, at you know, normal pressures in a laboratory, would that substance sublime? Or would it melt and boil? Right? You could look at it. So let me find one and we'll write it up there. All right, here's not the greatest phase diagram for carbon dioxide, but you know, it's usually not drawn to scale anyway. If you drew it to scale, it would be much harder to read. Okay, so this is not drawn to scale, so don't freak out if that doesn't look linear to you. Okay, so we've got the pressure in atmospheres on the y-axis, temperature in degrees Celsius on the x-axis. Got my sublimation curve, fusion curve, vapor pressure curve. Right. So what I want you to do is, based on looking at this solid, liquid, and gas phases, this would be a typical quiz question. Here's a phase diagram. I probably wouldn't put those in there, right? I would want you to know where solid, liquid, and gas phases are. What is the critical temperature? What is the triple point temperature? And what is the normal sublimation point? Okay, so pause it and do that real quick. So you got to know which is the triple point and the critical point. Now remember, the critical point is the end of the vapor pressure curve. So that would be right here. So this is my critical point. Let's do that in purple. No, let's do it in red. So that's my critical point. This is where all three phases coexist. So that's my triple point right now. So if I take an isotherm down from the critical point, you'll hit about 31 degrees Celsius. Take the triple point, take an isotherm going down, negative 56.7. It would be hard to give you one that's to scale that you could read up. Maybe I could give you a fictitious one that's drawn to scale so you could try to eyeball it properly. But I couldn't give you like a real substance. It wouldn't be drawn to scale. And then normal means at 1 atmosphere. So take a look. The 1 atmosphere is below the triple point, which means if you're in a laboratory and you're heating it up, it'll never melt. Okay? It'll just go directly from the solid to the gas phase like dry ice does. Right? That's why it's called dry ice. Carbon dioxide is called dry ice because it kind of looks like ice if you've ever seen it. Don't hold it in your bare hand. But it becomes a gas and never gets wet. See what I'm saying? So it never turns into a liquid. So that's where the old name dry ice comes from, which can be a little confusing because it's not really ice. So if we take an iso bar across at 1 atmosphere, we intersect with the sublimation curve and it goes from a solid to a gas at negative 78.5 degrees Celsius. Now, of course, if I'm at a different pressure, if I'm at half atmosphere, of course, that would sublime at a different temperature. If I'm up here, if I get up above the triple point, then it'll melt and then turn into a gas. If I'm way up, it'll melt and then go straight to a supercritical fluid and never turn into an actual gas. And that's how you can get that supercritical fluid for CO2 that they use to decaffeinate, things like that. So you got to be at really high pressures above the critical pressure, which if I gave you this value, you could read this across and give me the critical pressure, right? Same with the pressure at the triple point. But if I'm at temperatures above the critical point, right, up above here, I got the supercritical fluid. So pretty simple to do. So what I want to do now is water. Water's a prototypical one you're always going to see. Water's a little different because the fusion curve actually has a negative slope to it. That's got some repercussions for it. And it's got lots of different phases of solid, right? So it's called polymorphic. Let's take a look at ice real quick. Good luck drawing this, right? And this is not as complicated as it can get, but follow it. Some phase diagrams can get pretty crazy. So this is not drawn to scale at all. Normally we wouldn't even bother with this. So at normal laboratory stuff, we would just draw the typical solid, liquid, gas phases, right? Or states. But if you go up to super high pressures, you start to see different phases of the solid. So when you see molten, so we have ice 1, ice 2, ice 3, and there's like ice 4, ice 5, ice 6, as you get higher and higher pressures. This is called polymorphic or polymorphism, where you have multiple phases of a solid. So that's why I wanted to do water, to show you that term. Don't run into it very often, but if you see it, you go, whoa. And that's why you can't technically use state and phase interchangeably, although we do all the time, right? So you've got the solid state, liquid state, gas state, but you've got multiple phases in the solid state. Oh, you get what I'm saying? So let's read this. So let's take a look here. So we've got the liquid here, gas here, all the different phases of solid in here, ice 1. Typically, we only have run into ice 1 in our experience, right? Because we live life around 1 atmosphere pressure, okay? So let's take some iso bars across at 1 atmosphere. Let's take this across. Let's see what happens. Boom! Crosses the fusion curve. So it starts to melt, and if we bring that down, that would be your normal melting point, which we know is 0 degrees Celsius, right? And if you keep going, because the triple point's below 1 atmosphere, it's not going to sublime, right? So we keep going, heating up the liquid, bang! We hit the vapor pressure curve. That would be our normal boiling point, which we know is defined exactly as 100 degrees Celsius. So we can read the normal melting point and boiling point off of this, even though it's not drawn to scale at all. But if you want to get up to some of these higher pressures, I mean, we're talking about 2,045 atmospheres. Yeah, not going to run into that in the lab. You can get other triple points. So you have a critical point here, all right? So here's our critical point. And so this would be our critical temperature, critical pressure right here. You could read those off the graph. But you have more than one triple point, don't you? You have the triple point here between ice 1, the liquid, and the gas phases. But you've also got like a triple point here between ice 1, ice 2, and ice 3. A triple point between 3 solid phases. Right here, you've got ice 1, ice 3, and the liquid. What's getting crazy? Polymorphic substances. So this, I was thinking about when I was getting my PhD, a possibility was to go to Greenland and drill ice cores. I thought that was fascinating. So if you're drilling down a couple kilometers of ice, the ice on the bottom is under way higher pressure. So I don't know for sure, but it would have been interesting to see as you pull up this 2+ kilometer long ice core, when you're taking slices of ice from the top at the much lower pressure, at the very top, 1 atmosphere, down to the very bottom. I wonder what the pressure is, because that's a lot of weight of ice pushing on that. So I wonder at the very bottom of that, if you're at pressures high enough to get different phases of ice, and if you look at a slice from the bottom, would it actually look different because of those higher pressures? Maybe you have ice 2 or ice 3 or something like that. I don't know. That's something I haven't bothered to look into, but it's fascinating to think about, where I might have run into different phases of ice at the very bottoms of those cool ice cores. Didn't do it because, I was born in Minnesota. I didn't want to go to Greenland. I came to California. Sorry. But it was tempting. I think that'd be fun to go up and drill those ice cores and, take those ice cores, and it has bubbles trapped from ancient atmospheres, right? You can take a slice from like 1020 AD, and these little bubbles of the atmosphere trapped in there. You can crack that up and measure the composition of the atmosphere from 1,000 years ago or 10,000 years ago. That's so cool. Chemistry is so cool. So lots of fun. Now, one interesting thing about water, most substances, you're going to see the fusion curve straight up, right? If you're at normal, typical pressures, it'll just be straight up, maybe a slightly positive slope. But with water, it's slightly negative. What? Very few things do this. What the implications of that is, as you're increasing pressure, your melting point is changing, right? As you're increasing your pressure, your melting point's going, can you see it? So as I go up in pressure, the melting point's going down. If it's a positive slope, the melting point would go up. Interesting. But if it's a straight line, the melting point won't change much with pressure anyway. That's typically what we'll run into. So we can make that assumption in our class. Under normal pressures and stuff, melting point's not going to change much with pressure between the solid and liquid. Another aspect of that, if you're increasing the pressure, you're decreasing the volume, which means the density is going up. So as you go, for example, from say here, and you go up to there, as you increase the pressure, you go from a solid to a liquid. That's not normal. Normally, if you increase pressure, you go from a liquid to a solid. So what happens in that scenario is the density of the liquid is actually greater than the solid. What? That doesn't make sense. So ice, as you know, ice cubes float because of that negative slope. That makes the density of the solid less than the liquid, right? If you have a positive slope, that the reverse of that, most things, the solid's more dense than the liquid and it sinks. So water's such a unique substance with the hydrogen bonding and the negative fusion curve, sloped fusion curve. It creates really unique things. You can have a lot of fun, play with the phase diagrams. I can put any substance on there. I can put fictitious substances on there. I can travel along any isobar, any isotherm, up or down, back and forward. I can take you in squares and circles, and I can say, what phase is it? What transition occurs? What's the normal melting point? What's the normal boiling point? Does it sublime at sea level or 1 atmosphere pressure, or does it sublime, or does it melt and then boil? Lots of cool stuff. Phase diagrams rock. Now, these are simplified ones. They can get really, really I've seen some ones where even I'm just going, oh, my brain, right? And these are pure substances. What if you have mixtures? It gets really crazy, but this is good introduction into phase diagrams. All right, if you understand this stuff, so I practice it, right? While you're eating breakfast or lunch or something like that, just start drawing off the top of your head phase diagrams, figure out where the different phases go, and play around with stuff so you're very familiar with it. You can do this.